Hello, hello. Is it because my handphone is nearby? Hello, no. Am I clear? Am I clear now? Okay. So, thank you very much, everyone, for. Sorry. Uh, sorry, I have to figure out which one. Okay. All right. Uh, Thank you very much, everyone, for joining this session this afternoon. We are at the 5 o'clock point, and I think for everyone, this is almost close to the shutdown time. But just bear with us for a little while because what we've lined up for this afternoon are a few papers that is no less interesting in themselves. And the theme for this afternoon is the industrial session. And we've got papers from various background whereby we can share or have a look at how some practical application of the fundamentals of engineering and software or tools in the daily problem solution. Okay, so without further ado, I would like to welcome our first presenter from the Petronas Group Technical Solutions, Ms. Nur Arnida Abdul Talib. She is currently the staff engineer and her expertise is in methane emission. But this afternoon, she's going to be sharing a presentation entitled Identification of High Surge Pressure in LNG Loading Line System and Mitigation Strategy. So please welcome Ms. Arnida.
Assalamualaikum and a very good day to all of you. My name is Nur Anida binti Abdul Talib. I'm a staff TP in Process Simulation from Group Technical Solutions, Petronas. And on behalf of the co-authors for this paper, IR Fazrul Izwan Muhammad Ali, as well as Siti Fahana Muhammad Sha'ri, I'm going to present our paper entitled Identification of High Surge Pressure in LNG Loading Line System and Mitigation Strategy. For the introduction, understanding the challenges posed by a potential safety risk due to surge occurrences may be the first step in incorporating HSE prior to the construction of a new facility in this real LNG plant example. A pressure surge in piping systems can be caused by a fluid in motion forced to stop or change direction suddenly, or in other words, rapid momentum change, and also due to the cavitation effect. And in the diagram below is a typical LNG loading line system where the LNG is pumped out from the tank to the loading lines and finally to the jetty where there are loading arms and the ESD valves. This is the methodology adopted to identify the high surge pressure in LNG loading line system. There are 4 in overall. So number 1 is the dynamic model development, which includes the simulation of existing and new tie-in of LNG transfer facility. Number 2 is the model tuning, matching PTR data. This is very crucial as we match point-by-point pressure node with the pressure recorded in the PTR data. And number 3, search analysis on existing LNG facility, where this search analysis is based on the current ESD setting, which has incorporated high surge mitigation measures. So these high surge mitigation measures are the immediate opening of the kickback valves as well as the loading pump strip delay. Number 4, search analysis with the new tie-in facility included. And the search analysis is based on the same current ESD setting which has incorporated a high surge mitigation measures. And finally, number 5 is the potential increment in LNG loading with the new tie-in facility. So we're going to find out the maximum loading rate achievable. Just to highlight on the ESD2 activation sequence, so these are the sequences. Number 1, where the kickback valves immediately open, and number 2, the shutdown valves will be closed according to its stroke time, and number 3, the loading pumps will be tripped. As part of the methodology is the simulation modeling of the LNG loading line system. So the loading from 3 LNG storage tanks, which are furthest from berth, as longer distances are anticipated to lead to higher surge pressures. Hence, the modeling battery limit is pumped at LNG tanks up until the loading arms and including the ESD valve at the new tie-in facility. We have come to the results section where we run 3 cases. So for case 1, ESD2 is initiated with loading operation to jetty, existing facility only, and subsequent ESD actions take place by sequences. So the sequence can be seen clearly from this chart here. So ESD valves are closing based on its stroke time, and all the kickback valves are opened immediately. And finally, the loading pumps are tripped 5 seconds after the ESD1 valve is fully closed. And from case 1, the findings are the highest surge pressure is about 88% from the design pressure limit, which is seen to occur at the upstream of ESD2 for this case, which is in blue color line. The pressure then vacillates for a few seconds before they settle at the final steady state pressure of about 28% from the design pressure limit. Continuation on the findings for case 1. Pressure surges more than 50% from design pressure limit are also seen to occur at other locations in this simulation case. As can be seen here, for example, at the upstream of the kickback valves, where the surge pressure is 56% from design pressure limit, and also the mixing point from the pumps of the tanks, the surge pressure is 61% from design pressure limit, and even further upstream of the ESD valves, the surge pressure is 81% from design pressure limit, and the highest pressure, as can be seen in the trending in the previous slide, the surge pressure is 88% from design pressure limit. Okay. For case 2, ESD2 and the ESD of new tie-in facility are initiated with loading operation to jetty as well as the new tie-in facility, and subsequent ESD actions take place by sequences. So the ESD actions are the same as I mentioned previously, where the kickback valves immediately open, then the shutdown valves will be closed based on their stroke times, and finally the loading pumps will be tripped. The findings for case 2, the pressure surge for all scenarios are less than piping design limit and poses no threat to the system. Pressure surge is higher at upstream of ESD1 valve, about 1 bar difference for scenario where both ESD new tie-in facility and ESD2 initiated simultaneously as compared to ESD2 initiation only. Pressure surge is seen higher for the scenario where ESD new tie-in facilities valve stroke time is 5 seconds as compared to 15 seconds. This is due to the shorter duration and closing time of the valve. And for case 3 is the maximum loading flow rate achievable with safe ESD actions in place. The findings: total maximum flow rate from LNG tanks with acceptable surge pressures. There are two scenarios here. Loading to berth the existing facility only. So the percentage increment in loading flow rate is 17%, and the maximum surge pressure is 91.2% from the design pressure limit. Then second scenario is loading to berth and the new tie-in facility. The percentage increment in loading flow rate is 20.6%, while the maximum surge pressure in percentage from design limit is 90.6%. Allowable flow rate is higher for the scenario where loading operation occurs simultaneously to berth and new tie-in facility as compared to loading to berth only, and this is due to the additional new tie-in part section inventory would allow the surge to ripple away, thus taking away some of the force to the ESD2 valve. We have come to the conclusion section. In summary, the findings based on surge simulation and analysis confirm that high pressure surges are credible to occur at multiple locations at the LNG loading facility during ESD activation scenario. Point number 2, it is crucial to identify the potential locations and also the magnitude of the high surge to ensure that it is acceptable and below design pressure limit. And last but not least, this is to prevent LOPC by ensuring the SD settings are sufficient to handle possible pressure surges in case of ESD activates. I guess I have come to the end of my presentation. So, thank you for your attention.
Okay, thank you, Ms. Linda. So, a bit heavy for an afternoon session, but yes, that's what industrial session is about, which is, the application of the fundamental knowledge of chemical engineering. And I forgot to mention that the paper was co-authored also by Ms. Siti Farhana from MNNG, and as we see, presented here by Ms. Anita. So for the attendees of this session, you may drop your questions in the discussion forum column by clicking on the discussion forum bottom at the bottom there. And if you have any questions, you may just be there, and we'll try to pick. If there are many questions, we'll try to pick one that can be covered within the 5 minutes of the allocated question and answer session time. Okay. Okay. Anida, we have a question from one of the attendees. The question that's asked is, what is the biggest challenge in modeling search analysis?
All right. Thank you, IR Faisal. Okay, the biggest challenge will be in modeling it using appropriate software. Okay, I hear myself like
Echo, is it?
yeah, echo.
I think you need to turn off the speaker.
Okay. Turn off. Right. Okay, let me. Do you hear anything or nothing?
Now it's okay. There's no echo.
Okay.
Yep.
All right. Okay, so the biggest challenge is to find or to identify the magnitude of that surge pressure. Because that pressure is we're going to compare with the design pressure limit for the pipelines. Okay.
Okay. So thank you very much, Ms. Anida, for the question. I think we can only answer one question. So we are also a bit behind with the time. And I guess we hopefully will be seeing you again in the next ESCON
All
ICP.
right.
Okay, thank you. And next in the agenda is the next presenter is Dr. Zulfan Adiputra. He'll be speaking uh, on the presentation topic of the development of dynamic simulation of gas and condensate pipeline network. About Dr. Zulfan, he's currently the modeling specialist in the group solution of Petronas. And this is his first presentation under group technical solutions, as previously he was working with university. Okay, so I welcome Dr. Zulfan Putra to present his paper.
Hi, good morning. This is Zulfan with Zarina and Shahrul Azman from Petronas Group Technical Solutions. And the presentation for today is development of dynamic simulation of gas and condensate pipeline network, the work that we've done, I think, last year or 2 years ago. The outline of this presentation is about the, I will share a little bit on the Malaysian Peninsula Oil and Gas Pipeline Network, and then the methodology that we've done, some data assumptions and boundaries, and then some results and discussions that we can share, and then lastly, the conclusions and the way forward. This is basically the Malaysian Peninsula. We have on the eastern coast, we have all of these gas sources, platforms and whatnot, and then with hundreds of kilometers of pipelines commingled together on the shore here in Kerteh and Terengganu. So the problem is that we like currently running that. So so the operations need to know what happens if one of the platforms then shutting down, and then can we then make like a reliable productions, how then evaluate the productions, the impacts that can happen. So what we did is we gather data like components and then the compositions, temperature, pressure, and flow rate, and then we gather the length and the sizes, and then the network situation, and then we use icon symmetry or simulation software to develop the dynamic model of the pipe network. It's using the network solver, and then we do the model validation using the data in 2018 December, and then we use this model to predict the situation in January 2019. So basically, then this is then for the validation, this is then for the predictions, and then we get some insight on the evaluation of the system. So basically, we have like in simplified mode here. We have this section A, section B, section C, different platforms, and they're commingled here in the OSC, OGT, and NT gas, and then from here they then send through this whole pipes into the several gas processing plant. The way that we validate this gas composition is then by means of the matching density. So because the heavier part, which is then the C6 plus, we don't know. So by using the densities measured, we then vary the properties of the C6 plus in such a way that we can match the density, and then we can then use it for the subsequent evaluations. This is some of the results that I can share. So this is an example on how it looks like in the icon symmetry. We have the pipes, and then we have the commingles, and we have the separator, and then we have the gas produced, and then we have the liquid also produced, or the condensate, as we said. And this gas is basically then going to be sent, or what they use the phrase of export. So we can see this is then the gas export. This is then the December 2018. sorry, this is then December 2000. This is December 2018. We have the symmetry model in the blue lines, and then it's matching nicely with the data, the green line. And the red line is just another model developed by third party for us to evaluate. And then using this model, we then how do you call it, predict what is then going to happen in the month of January. So we predict it to be like these blue lines, and then the red, the green line is then the data. So we could see that for this particular area, the predictions is consistently lower. So this could be due to because this particular area, it has some like a gas processing, like a membrane separation unit. So it has this fixed removal ratio that we employed based on the validation. So apparently they did something like a manual operations, which makes the there's this consistent error throughout the period. In another plot that we can predict the condensate produced. Like in this case, we have the condensate produced. So on the field, there is no such measurements on how much condensate is being produced. They just know that the level goes up, and then they just open the valve. And then if the level goes down between this 15-20% or to the percent even, they will then close the valve. Yeah. So this is what we could predict based on these C6 plus properties that we tried to match. And then we could see that in some periods we have lots of condensates, in the other periods we don't have lots of condensates. So basically this could be used like a guidance on if the properties of the C6 plus is constant throughout the period, and then they could use this as a guidance to anticipate how much liquid is coming, and then how much liquid is then needs to be transported or diverted and whatnot. So we now conclude that this dynamic simulation has matched with the has been tuned to match the actual productions, and then the accurate properties of the pseudo component of C6 plus are very important for the condensate product predictions. And then the model now is currently being used by the upstream department. Yeah, so they're now improving this model, and then they use this for their like scenario evaluations. If one platform shuts down, and what is then the effect to the other platform, or the effect to the commingle lines, and so on and so forth. Is the pressure goes down, and then how long, and then the estimations of if we have like a CO2 breakthrough in the platform, how long do we expect that CO2 breakthrough comes into the processing plant? So with this, I conclude the presentation. So thank you very much.
Thank you very much, Dr. Zulfan, for the recorded presentation, I think.
Very quick, yeah.
And okay, we have a question, very quick one from the floor. The question goes: what is the best way to represent the initial conditions in a pipeline, for example, a liquid hookup, before running a case study?
The best condition is to say it again.
You get the question?
No. What is then the best condition to?
What is the best way to represent the initial conditions in a pipeline before you start a case study in the model?
Initial conditions on the pipeline. So this is then one of the few events that because this pipeline is hundreds of kilometers away from the shore, yeah? And there is no like sensors, anything that can monitor or see what's inside of the pipeline. So this is then one of the few moments that I would say, oh, so nonetheless, so what we did last time was we just a simple methodology that we validate the model based on the data. Like in this case, it's December 2018, and then that we tune the necessary parameter. And then we use that model, And then we assume, it's a big assumption. So we assume that at the end of December 2018, that is then the starting point. And then when the data of January 2019 came, we can just plug in the data and then see how the plant responds.
Thank you very much, Dr. Zulfan. I guess you pretty much answered that question, how you prepared or get the model before you run the necessary case study, right? The cases that you need to analyze.
Yeah.
And yes, we move ahead. Thank you very much for the presentation, Dr. Zulfan.
Thank you.
Again, we hope to see you in the next ISCON event.
And
okay, the next presentation will be carried out by Rahim bin Norman, who is from Group Technical Solutions as well. He's currently a staff engineer with a lot of focus or emphasis in his work towards asset digitalization. Okay, and the presentation that he's going to be sharing this afternoon will be entitled Load Shedding Operational Analysis Using Dynamic Simulation at a Fertilizer Plant. Okay, I welcome Mr. Rahim Norman.
Assalamualaikum and a very good day. I am Abdurrahim Norman from Petronas and I will be presenting steam system load shedding operational analysis using dynamic simulation of a fertilizer plant. A little bit of introduction. A steam system operation of a fertilizer plant can be very complex, especially for a plant that has undergone multiple revamps over its lifetime. This is due to tight steam supply capacity margin, which requires plant shutdown when a single boiler trips or undergoes maintenance. There is also high interdependency behavior between steam users, which creates sort of a domino effect of disturbances and trips. The plant has 2 existing boilers, and with the installation of a new third boiler, it will provide additional capacity margin and operational flexibility. This presentation will focus on the transient analysis of the steam system to establish proper steam load shedding management with 3 boilers in operation. This tree network diagram is the simplified process flow diagram covered in this simulation study. We have the boiler feed water and the fuel gas network, where additional line is designed to supply the boiler feed water and fuel gas to the new boiler. And for the steam system, the steam from the new third boiler joins the common HP header before being let down to MP and LP headers accordingly. There is a total of 19 main steam users for the fertilizer plant in the steam network. Let's move on to the methodology of this simulation study. We are performing dynamic simulation using Icon Symmetry software. It is a process simulation software which is commonly used for transient analysis. And for the property package, we are using Steam 97 for the boiler feed water system, as well as the steam system. And for the fuel gas system, we are using Advanced Pang Robinson. We then develop a base case simulation to match existing operating conditions for a selected historical period. The selected period fulfilled the base case criteria, which are stable plant operation with normal operating load and low steam imbalance operational figures. The actual operating conditions are extracted from pi from the plant. The model managed to achieve static accuracy within plus minus 2% of the instrument range. As for the equipment modeling approach, all of the equipment within the battery limit are modeled with the intention to represent actual equipment behavior as close as possible. The most important thing is representing the actual plant hydraulics, and this is incorporated by extracting piping configurations, for example, the pipe diameter, the length, the undulations, and all the fittings from available plant isometrics into the pipe segment unit operation in the model. For the control valve, actual control valve properties are also incorporated by extracting relevant information from the datasheet. This includes the valve characteristics, actuator stroke time, the CV curves, and also fluid choke curves whenever applicable. Now for the steam users, we model the steam turbine using an expander unit operation. And this is the same unit operation is used to model the induction, extraction, and condensing steam turbines in the steam system. Due to unavailability of turbine datasheet, as this is an aging plant, we adopted the radial design point model, which uses efficiency correction curves from vendor data, and this is normalized against user input design point, which is obtained from the base case simulation model. The inlet guide vane area percentage is used to determine the steam flow rate across the turbine, and this is governed by the pressure and flow relationship, which is the K value, as shown in the equation on the bottom right. As the process side is not covered in the simulation scope, a simplified turbine model has to be modeled by regulating the IGV to maintain the desired power output. The diagram on the right shows an example of the simplified turbine control system for one of the extraction steam turbines. Now let's move on to the pumps. We have the high pressure boiler feed water pump, and this is modeled as two pumps in series to represent the mid-stage boiler feed water extraction. The actual pump performance head and efficiency curves are incorporated in the pump unit operation. The affinity law, as shown in the equation below, is used to create the pump performance head curves, as shown in these pump curves, to create like a performance curve profile at varying speeds. As for the boiler, it is represented as a simple heater unit operation with fixed pressure drop and outlet temperature. The boiler feed water supply enters the boiler, and the same amount exits the boiler as high pressure steam, and it is integrated directly into the steam network system. Moving on to the process control and trip sequence. All process control configurations are modeled using actual or best practice PNID tuning parameters to represent the plant's control behavior. The three separate network models are integrated based on two main integration control philosophies. The first one is the boiler integration control philosophy, which is shown on the right, and this relies on the master pressure controller located at the high pressure steam header to automatically regulate fuel gas and boiler feed water flow rates to maintain HP header pressure. The second one is the boiler feed water integration control philosophy, and this relies on a master pressure controller at the pump discharge outlet to automatically regulate steam turbine power delivery and pump speed to maintain pump discharge pressure. As for the trip sequence, it is being programmed using the event scheduler function in icon symmetry to define sequential events following an upset condition. ESD interlocks, controlled RAM rates, as well as manual intervention actions are incorporated in the dynamics model based on our discussion with the operators and their experience input. Now let's move on to the case study and its results. We performed 4 different case studies to evaluate the transient behavior under different upset scenarios. The range of upset scenarios cover steam supply disturbances, steam user disturbances, as well as operational disturbances. The first case study is to trip one boiler, which is the steam supply. When one boiler trips, the remaining 2 boilers have to ramp up the production rate from 67 to 100%. Case 1 results prove that the new system's operability is adequate to prevent further trips to crucial equipment in the plant. Having said that, 2 less crucial steam users needs to be automatically tripped upon boiler trip to minimize the impact of pressure fluctuations. The graphs below show the pressure fluctuations are within allowable limits and stabilizes after several minutes. The second case study is to trip the main standalone steam turbine at HP header. So this is a steam user trip. As the demand drops when the steam user trips, the 3 boilers are able to ramp down quick enough to prevent steam system overpressure. There are no direct disturbances to MP and LP steam supply when the standalone steam turbine trips. Therefore, the MP and LP header pressures are relatively stable as shown in the graphs below. Now the third case study, it's also a steam user trip, but we are tripping the main extraction steam turbine where this provides the MP and LP steam to the MP and LP headers. And so the minimum MP header pressure, which we observed during the case study, it's too low to continuously supply MP steam to the steam reformer, which will cause a major plant trip due to steam carbon ratio disruption. As you can see, the pressure dropped from 43 bar at the MP side to around 35 bar. And the minimum was about 38. The minimum limit was about 38 bar. Case 3 simulation results are consistent with plant's historical events. When we consulted the operations, they mentioned to us that for the past few years, a similar event happened where the main extraction steam turbine tripped and it actually tripped the steam reformer. So what we did using the dynamic simulation is to try out many scenarios and many interventions, and we came up with an operational strategy to minimize the impact and prevent total plant shutdown. The last case study is to analyze the impact of operational disturbances by accidentally starting up the spare boiler feed water pump. The accidental pump startup will cause a temporary pressure spike at the discharge line. The results show that the boiler feed water cascade control system is able to minimize the pressure spike by regulating the steam turbine drivers to reduce overall pump speed. The maximum pressure observed is below piping design limit. As a conclusion, the results prove the three boiler arrangement can sustain the fertilizer plant's continuous operations. Operational strategy can be developed together with operations team using dynamic simulation. It is also important to note that dynamic simulation can be very useful and beneficial in providing the project team with important recommendations to ensure correct boiler integration design and smooth plant operations. For future work, the dynamic simulation can be further improved by modeling the boilers with high fidelity, which includes the steam drum, fuel gas combustion, heat exchangers, and the associated three-element process control, namely the flow, pressure, and level. This will further improve the accuracy of the transient analysis results. That is the end of my presentation. Thank you very much.
Thank you very much, Abdul Rahim, for the very descriptive presentation on boiler dynamic simulation. And I think we also have we also have Asfar from the very plant itself, Petronas APF in Bintulu. And he will be complimenting Abdul Rahim Norman for any questions that the attendees are interested to ask. Okay, I have a question. The LP header seems to be fluctuating a lot more compared to the other header in case 1. And the poser of this question, Dr. Zulfan, would like to know why is the reason for that?
Well, Rahim, would you like to answer that one first?
I think can you hear me?
Yeah.
If you look at the graphs, I think Dr. Zulfan, it's more on the scaling, because LP is very small, we scale it very big, so I think the fluctuation is big. But from our case study 1, there was actually no issues in terms of the fluctuation in HP and LP.
Yeah. If I may add, based on our experience in plant as well, it's because we have a separate controller that is actually controlling the LP header that is in one of our turbine equipment. So yeah, it's actually reacting against that disturbance due to the plant due to the boiler trip, and that reaction actually causes further escalation of fluctuation that you can see in the result as well. This is actually quite true based on experience from our operators at field. So they normally prefer not to have that control actually available. They will rather control it through another means, which is to just vent out the excess steam so that the disturbance can be reduce and allow for better for flatter behavior of the LP steam header.
Explanation. Yes, I think for anyone who's done a lot of simulation, especially dynamic simulation, being able to match the nuances and disturbance of the plant, and being able to replicate the behavior of the plant in that transient moment is something that is quite a very challenging thing to do. And yes, I think that was quite some effort to go and match the plant behavior with the model tuning and everything. Okay, and if there's no more question, I would like to express my thanks to J. Rahim and J. Asfar for sharing this session with us this afternoon. And we hope to see you in the next session of the ISCON event. Okay, thank you very much.
Thank you.
And moving on to the next agenda this afternoon, or the next presentation this afternoon, is by the custodian of process simulation in Group Technical Solution, Tuan Haji Hasno bin Hashim. And he's going to be sharing on a topic about fluid characterization in his presentation entitled The Application of Piona Characterization in Refinery Process Modeling. But I hope it won't compel everyone to start singing a song that is similar to that Piona sound. And so I would like to welcome Raji Hasno to share his presentation this afternoon.
Today, I'm going to talk about Piona-based refinery process simulations. My name is Hasno Hashim from Petronas Group Technical Solutions, Malaysia. So my presentation contents, we touch on 6 points. First, on the refining process background. Second, on refinery fluid characterization, mainly boiling point-based characterization and Piona-based characterization. And I'm going to discuss on the sample application using icon symmetry. And lastly, results, discussion, and conclusions. Refining processes is basically the process of splitting and deploying and purifying crude oil into various different products, ranging from light gases to solid coke form at oil refineries. Inside refineries, there's various combination of reactions to upgrade the crude oil to a highly valued products. A simple separation refinery is called a topping or hydroskimming refinery, while refinery, the complex upgrading processes is called a full or deep conversion refinery. So from the right diagram, you can see that the various unit or process operations that are available in this refinery, starting from the left, where you have the atmospheric distillation columns, basically do the first fractionation into various cuts, and it goes, for the top portion is mainly light gases. We go to the gas processing units, where it's separated the LPGs and butanes and also refinery fuel. And as we go down from the top column to the bottom of the atmospheric column, the products from light naphtha, heavy naphtha, jet fuel, kerosene, and diesel oil and gas oil, the density, the weight of the products getting heavier. And the bottom atmospheric distillation is sent to the vacuum distillation units, where further separation under vacuum conditions takes place to yield vacuum gas oil. And the bottom is mainly vacuum residue is sent to a delayed coker, where is to produce petroleum coke. So you can see that this is the configuration of full conversion refineries. There are various units of operations that either fractionate or transform the molecules of the cuts from one structure to the other. So this is a very complex process, and it's a very challenging process to model in the commercial process simulators. So like I mentioned, the refining processes can be categorized into 3 types. First is separation, distillations, and absorption. From here, basically separation is splitting up the molecules into various cuts based on boiling points. Then next type you have conversion, where it's thermal conversion or catalytic conversion. This is basically the products or the cuts of the refinery product is changed to a different type using reactions via catalyst. Basically the change in molecular structures, whether it's getting from a straight chain to a branch chain or a cyclic chain, depending on requirement of the refinery products. And last is basically treating using hydrogen and solvent, basically mainly to remove sulfur and nitrogen compounds, and to meet the emission limits, especially for products that they're going to use for fuel. Refinery freight characterization. Crude oil basically contains a complex mixture of hydrocarbons, organic sulfurs, and nitrogen compounds, and as well as metals and oxygen. And the hydrocarbon compounds can range up from a C1 molecule up to more than C70, and can consist of straight, branch, and cyclic structures. Like I mentioned, you can see in the picture below, you can see the crude oil consists of hydrocarbons and non-hydrocarbons, and they have various structures, be it a straight chain, branch chain, and cyclic. So these combinations make the characteristic or characterization of crude oil is very challenging. And from the right, we can see how the distribution of the carbon numbers, is the top product have the low carbon numbers. As we go to the bottom of the atmospheric column, we can see the heavier the product, the number of carbon numbers increases, as well as the complexity in terms of structure. There's a number of components crude oil can go up to more than 100. So normally it's not practical to define crude oil combustion based on individual components. Normally, if you model a petrochemical processes, normally consists of maybe C1 to C5 components, either alkanes or alkenes. You can basically specify exact component, for example, methane, butane, and butane, isobutane, etc. But for crude oil, it's impossible to do that, because you have more than 100 plus separate components, and the structures, the various structures that that need to be defined, and also the lab analysis that is done on crude oil doesn't go into that such detail. So the best option to basically characterize fluid characterization is through boiling point ranges, that basically is based on cuts, when you based on either true boiling point or the DT6 analysis. Basically, you based on different temperatures, you define the percentage of distillation from 0 volume percent to 100 volume percent. In addition, we can also include the bulk density, also additional data, sulfur viscosity curve. You can input the crude oil definition. So on the right is basically a sample of crude oil assays. You have your bulk information, basically density, specific gravity, the sulfur content in the bulk, as well as you can see here the volume fraction, the temperatures for volume distillation. From boiling point based characterization, we basically specify or input the boiling point based ranges, and normally we use a set of 40 to 50 pseudo components to represent the whole crude. So basically what we're doing is basically partition the crude oil into a discrete molecules. Each molecule behave like a pure component behavior, which have its own molecular weight, densities, critical parameter, temperatures, pressures, and volume. And basically that's how we're going to characterize the crude oil. It will work fine if you just want to do a simple simulation, but however, using just a typical boiling point based characterization, it's not able to capture the different level of molecular structures, which basically will affect certain refinery products properties, for example, RON and cetane, which is critical for refinery products specification. So therefore, we need to improve or enhance the characterization using Fiona base. Basically we need to characterize the crude properties into to reflect is the molecular structure from paraffin, paraffin, olefin, naphthenic, and aromatic structures. So when we look at an analysis that take into account Fiona, so we can define it much further in the term of the components or basically structures, the different kind of structures based on the analysis available. So using the available information, we can develop a Fiona-based characterization in the process simulator. Basically, we have 5 groups, each group representing Fiona, Piona. So basically, we have 5 sets of pseudo components with separate boiling points, separate density information, and critical temperature, pressures, and volume. So using this approach, will be make the characterization of crude much more detailed and much more accurate. So we had a sample application using icon symmetry where a crude distillation unit was developed using both approach, the normal boiling point and also the Fiona fluid characterization. The feed is basically based on Arab-like crude, and so we are feeding it to the atmospheric column, and the bottom of the column is sent to a vacuum column, and top going to a naphtha stabilizer. So looking at the results, we can see that both boiling point characterization and Fiona characterization, the results are pretty close in terms of temperatures, in terms of duties, and also even the cuts. You can see the variance, is less than 10%. Some the exception of certain parameters, a bit more than 10, but still close enough to 10. So it means that purely for a crude column simulation, using Fiona doesn't really alter the results that much. As well as comparing bulk and thermal properties, we can see that again they are very close. The exception for enthalpy, the common enthalpy, due to a different way or the influence of the molecular structure towards how enthalpy is calculated. And also we can see that in terms of viscosity, there are slight improvement in terms using Fiona, especially towards the heavier component, using normal boiling point approach, as is going to as the heavy component, for example, residue, not able to calculate viscosity properly, but using Fiona is able to calculate a value. So comparison of refinery product properties, you can see that here the impact of Fiona, for example, you can see at RON and MON. For light naphtha, this the normal value for RON is 95 to 100 for light naphtha, which is naphtha is basically a component for gasoline blending. However, using boiling point characterization, the estimated RON is 1000 is not sensical. And also you can see that cetane numbers is very close together, and also the flash point and pour point, the variation is quite close. So from here you can see that the effect of Fiona characterization is heavily influencing the RON and MON calculation. So as discussion, the result from the column shows the very small variation between the boiling point characterization and Fiona characterization. Again, physical and thermal properties, yes, right. Again, the variation is very small except for enthalpy, because due to different bond enthalpies calculated based on Fiona molecular structure. As for the refinery product properties, the RON and MON has the big impact from Fiona characterization as compared to others. So in conclusion, the application of Fiona characterization for crude distillation simulation does not provide a significant improvement. However, when we try to model or proceed to model the reaction side of the refinery, for example, the FCC, so reform hydrotreater, which involve reaction changes in molecular structure, this is where the Fiona characterization will become handy and will provide a much better results. Thank you very much for your attention.
Thank you, Tuan Haji Hasno, for the bit heavy presentation in this late afternoon moment. But I guess there will be a few questions from the attendees who will be very interested to know more about this topic that you've just presented. And we've got the first question here from Ms. Azlin Azna from GTS also. Question goes, is there any disadvantage of using Fiona? And is there a time when we should avoid using Fiona when doing pre-characterization?
Okay, thank you, Session Chairman, for the question. One thing is, I would say, disadvantages of using Fiona basically introduce additional 5 slates of compounds. Each compound slate we have around 40 to 45 separate pure components, quote unquote, body points based on how you set up the initial characterization settings of in Fiona. And you can imagine if you have 40 components for each classes. So for Fiona, you already have 5 times 4 is 200 plus your pure component. C1s until, for example, C5. So if you're modeling a complex, unit operations, maybe unit wide or refinery wide, the simulation speed will go down because the simulator will need to compute all the flashes for these 20, maybe 20, 250 separate compounds, as compared when doing a bulk characterization. Maybe at most you get 50 to 60 different components. So that's one of the disadvantages that I see using Fiona. It will slow down the simulation speed when you are going towards larger and larger models. When you should not use Fiona, well, I think you should use Fiona at any time, provided you have the information in first place, because Fiona give you much more information on the molecular structures, and basically it will help to increase the confidence level of the simulation results as compared to just doing a typical characterization using bulk properties, which you might need to question the results. For example, you can also calculate RON, predict the RON based on bulk properties, but how sure are you on that results as compared to using Fiona characterization? Okay.
Okay, thank you. There's another question from the floor. What is the acceptable variance in practice when you are trying to actually match the physical property of the fluid as you model against what is measured in that?
I think a best practice, whether we are trying to match heat and material balance or we're trying to match actual plant conditions, I think anything less than 10% is considered a good match. Anything below 5 is excellent match. Again, you have to remember there are a lot of uncertainties. For example, plant instrumentation, there are uncertainties there. How the lab analyze the compositions. There are also uncertainties there, and also the differences between different simulation software. For example, the thermodynamic models, the way it estimate properties. There are a lot of uncertainties. So if you can get basically constrain all these uncertainties and get the results down to 10% or less, that's, in my opinion, is a very good acceptable variance for engineering usage.
Okay. Seems to be another one. I think it's a hot topic this afternoon. When you're talking molecular stuff, what are the typical measures if the discrepancies are more than 10%? Do you dispose of the data and get new sets, or is there a way to like fudge it or massage it?
Okay, I think that's a normal challenges faced by anybody trying to match actual conditions. You will have discrepancies more than 10%, and what you want to do about it. First, you need to check on your input data, whether you are taking a snapshots of data or an average of a certain period. So I think one of the best practices that we propose when we try to match actual, plant condition is we take much a longer time, and we take the average value and we remove the outlier, so we know that that's where the condition, the plants, it's stable, the mass energy is almost balanced, and that would help to reduce the discrepancies. Next, we need to make sure that our tropic models, for example, is the correct ones for the particular process. For example, if we are modeling highly non-ideal conditions, you need to select tropic models that is you will handle or cater to that non-idealities. For example, NRTL or Uniquac, as compared to you just use standard Peng Robinson of a box. So that's how you try to reduce the discrepancies by 10%. If after you do all this and there are still some discrepancies, so that might comes, it might highlight there's actually some issues. Maybe in actual plant, some equipment are not operating at their theoretical or close to theoretical or design condition. There might be some things happening actually in plants, and actually it's good. You can use this discrepancies to detect areas of the plant that basically have problems. So not necessarily all the models that you want to do you have to match have the accuracy less than 10%. Sometimes we accept above 10% because we basically telling us something is happening in the facilities. Okay.
Okay, thank you very much. I think that's all we can have for these presentations Q&A. Heavy stuff indeed, but yes, that's what chemical engineering is about. It's all about trying to imagine stuff at molecular level, which for some people is too much for them. Okay, and thank you very much, Tuan Haji Hasno, for the presentation. And as we move on, we're already 11 past 6, and we are supposed to have a presentation from a presenter from MLNG, but I think I've been informed by the moderator that the presentation has been cancelled by request, and so we skip to the sixth, sorry, to the fifth, to the sixth paper in the agenda this afternoon. Presenter is Ms. Farah Shamim Anwar, who is a staff engineer in Group Technical Solutions again. She co-authored this presentation with Mr. Das Babwa, Sharul Azman, and Dr. Sharul Azman, and Mr. Rafi Hadi. And the presentation is a time series model using hybrid first principle with operational data for optimization of an industrial endothermic reactor system. Okay, so without further ado, I would like to invite Ms. Farah to present her subject.
Assalamualaikum, salam sejahtera and good day. I am Farah Shamim Anwar from GTS Petronas. I will be presenting a paper on behalf of my team titled Time Series Model Hybrid First Principle with Operational Data for Optimization of an Industrial Dehydrogenation Unit. This paper will discuss the work done in an optimization effort in one of our hydrocarbon chain. Shown here is my presentation outline for today. First, we will go through the introduction, which elaborates some background of the process and the constraints of the process unit. After that, we will discuss a little bit on the methodology adopted in this work, which includes the general workflow and how data generation is done using first principle. After that, we will go through some of case studies conducted by varying several influential variables to observe the impact towards our monitored parameter. Then we will go through the conclusion, future work, and also acknowledgement section. As an introduction, I would like to go through a little bit on the chemistry of light alkanes dehydrogenation in general. Dehydrogenation process is a process of hydrogen removal to form olefins. An example of dehydrogenation reaction shown here is for propane and isobutane. These reactions are reversible and highly endothermic. For instance, a typical isobutane dehydrogenation is carried out at beyond 500 degrees C. However, due to this high temperature, the condition promotes cracking and Cook reactions, which gradually reduces the selectivity to the corresponding olefins. Excessive and uncontrolled coking into the screen will cause high pressure drop across the system, which eventually requires to be shut down for maintenance. This page shows a typical process flow of light alkanes dehydrogenation. Reaction takes place in n number of stages in series with interheaters in between. Catalyst is moving bed and the used catalysts are regened in the CCR. In the reactors, catalysts are contained by the screens. Cook formed from side reactions will accumulate on these screens. Over time, the screen will get plugged and cause high DP. The process unit can handle only a certain limit of DP across the system and needs to be shut down for a cleaning when the limit is reached. This causes the process unit run length to be very limited even though the catalyst has not reached its NH. This slide shows the simplified workflow adopted when carrying out this work. First is to collect multiple runs data and reconcile based on a defined criteria. More data is generated through first principle methodology. This is done through a process simulation software, Symmetry. Secondly, influential variables are selected based on process technology point of view, and reconciled data are put into classification into significant categories to simplify model inputs. With this data, model is developed. Third step is to validate the model with actual data input. Step number 2 and 3 requires iteration until fit into accepted tolerance. After obtaining a relatively good model, case study were conducted within the acceptable ranges from technology licensor. Optimum point is then identified based on a series of defined constraints. As operation continues, performance needs to be managed throughout the targeted duration. At this stage, periodic calibration may be required to update the prediction. This slide shows an example how the data generation by first principle. This is how we generate data on effective diameter based on actual input. Actual input is specified into process simulation software to generate effective diameter at a given timestamp. So over time, compounding Cook laydown can be derived from the changes of effective diameter. So we can observe even day to day, month to month, or a specified duration or frequency. This is a sample of a case study with varying load. Load is actually the throughput to the reactor. As we can see, throughout the duration, which is DOS, days on stream, we can see that the DP increases over time. So based on this case study, we can see that each step gives relatively low impact to the DP profile across the screen. So as predicted, higher load corresponds to more severe condition, hence resulting in high DP. This case study is showing the varying inlet reactor inlet temperature, RIT, towards the DP across the screen. So we can see each step size gives a medium impact to the DP profile across the screen. And higher RIT corresponds to a more severe condition. That's why higher RIT, the green line, eventually resulted in a higher DP across the screen over time. This is a case study at varying hydrogen to hydrocarbon ratio. We can see that hydrogen to hydrocarbon ratio gives a significant impact to the DP profile across the screen throughout the duration. So based on this plot, we can see that lower hydrogen to hydrocarbon ratio corresponds to a more severe condition. So in order to reduce the DP across the duration, higher hydrogen to hydrocarbon ratio is desired. This case study is for varying reactor inlet pressure. As you can see, the high, medium, low reactor inlet pressure line overlaps on each other. So based on this, each step size gives no impact to the DP screen profile. Conclusion. DP profile across the screen can be predicted through utilizing first principle model combined with analysis from historical data. This model enables the user to run the possible operating conditions and evaluate the estimated or predicted profile, which dictates the run length of the unit. Any process optimization study must comply with first principle and process technology know-how. Pure data analytic has high potential to mislead the results and also the findings. From the case study, the most significant variable that impacts the DP profile is the hydrogen to hydrocarbon ratio, followed by RIT, reactor inlet temperature, and load. However, in the effort to identify optimal set points, the case study has to account for combination of all the influencing variables. Future work, there are two main things that can actually give a significant improvement to the model. One of the main improvements that can be introduced is to complement the DP profile model with a yield prediction model in achieving the next level of optimization. Managing the constraints and maximizing the production needs to be balanced. The yield prediction model might have a common or overlapping set of influencing variables. So as one parameter can impact both of our constraint model and also production model. I think this is the end of my presentation. Thank you and have a good day.
Thank you very much, Ms. Farah. I understand that it's already close to 6:30, and I'm pretty sure that some of you must already be worn out by the long day. But I think we can go with one question for this presentation. The first one is the question is referring to the slide that lists the steps for the analysis. The interpretation, is it interpretation steps 2 and 3? What is the tuning parameter? Direction, I'm not sure. Sorry, I'm trying to understand. It's the interaction or iteration in step 2 to 3, what is the tuning parameter? I think the question meant iteration in steps 2 and 3.
Iteration. I'm not sure I understand the question. Probably it's relating to the step size. I think I need to refer back to the slide because the magnitude of each of the parameter is something proprietary. So it's quite sensitive data to be reviewed. I think that is the first reason why the skill is removed for each of the plot.
Okay.
Sorry, I'm hearing echo. Tak berapa.
Right. Okay. Okay. Moving on to the next question. Is high hydrogen to hydrocarbon ratio always desired? Does it have any effect on the yield if we vary the ratio?
Yes, actually, managing the constraint and also getting the right yield or the targeted production rate, it has to be balanced for the hydrogen to hydrocarbon ratio. Because if we increase, yes, we reduce the coking, but at the same time, it compensates to the yield production also. So yeah, in that sense, directionally for the production, low hydrogen ratio should be the right way.
Any more question? I think we can go for one more question. All right. Okay. If there's none, thank you very much, Ms. Farah, for the presentation and also to the co-authors of the paper. So we now arrive to the last presentation of the session. This one will be presented by IR Saiful Anwar Mokhtar, again from Group Technical Solutions. And he's going to be sharing a topic on optimizing for viability, revamping vacuum distillation unit in a brownfield project. Okay, so I welcome IR Saiful to share his presentation.
Hi, a very good day, ladies and gentlemen, wherever you are. I'm glad to be here today to present a paper on optimizing for viability, revamping a vacuum distillation unit in a brownfield project. The presentation will describe on how optimization could be applied to a brownfield project to optimize the scope of work, reducing modification and allowing the project to stay commercially viable. Before we move further, probably I could introduce myself first. I'm Saifullah Anwar Muhammad Mokhtar. I'm currently a custodian engineer at Petronas Malaysia. I'm a chartered chemical engineer of Icpeam and a registered professional engineer with the Board of Engineers Malaysia. I possess over 18 years of working experience in the refinery, gas and LNG as well as petrochemical industry. Okay, first, why optimization is needed for a brownfield project? Firstly, it always goes back to project economics. There is limited project budget. Doing project is always about reducing capital expenditure and getting the highest return back to the shareholders. Brownfield project always come with uncertainty. We do not know how the performance of an existing facilities or the equipment and what are the limitations. Hence, more often than not, leads to unforeseen scope modification or scope creep. So this scope creep will eventually add up to the cost of the project, hence impacting the project economics, making the project uneconomical. Then we will also have constructability issue. Building a new plant or facility inside an existing facility is not that easy as compared to a greenfield project. Thirdly, there is always utility limitation in the existing utility. Adding new equipment or scope will most of the time require new utilities. Apart from utility limitation, other supporting facility may also have their own limit. For example, in a refinery, this could be limitation in the saltwater treating unit or a limitation in an amine regeneration unit. And finally, there could also be limitation in the plant or the equipment adequacy themselves. So you see, these are the pain points that we normally encounter in a brownfield project, and all of these call for optimization to be done in a brownfield project to ensure that the project to be not only commercially viable, but also easily constructed and technically possible. On the vacuum distillation unit or video column that I was working on my previous project, the video column is designed to fractionate heavy LSWR into product streams such as light vacuum gas oil, LVGO or MVGO, as well as HVGO and vacuum residue VR. The original design operating pressure is 9 mmHg. The original design column inlet temperature is about 404 degrees C, while the design throughput was a 3.5 kilobarrel per day of LSWR feed. Essentially, the column is a typical 5-pack bed, 1 flushing section, and 1 stripping section. As for the revamp operating conditions, the video will need to be debottlenecked to allow higher throughput of up to 23 kilobarrel per day with lighter LSWR feed from the upstream parallel refinery. Also, due to the higher throughput, in order to allow for adequate separation within the column, a new fired heater was added upstream of the video column to provide additional 20 megawatt of heat duty to the video column. Hence, to meet the debottlenecking objective, not only the column received additional mass throughput, but it also received additional heat load to the column heat balance. Hence, like it or not, we need to optimize the operation of a video column when it comes to brownfield project. So how did we do this? Firstly, the fired heater coil outlet temperature or COT into the video column could be reduced from the design operating temperature to the lowest operating temperature at which the column is still able to allow good separation to occur within the column. This optimizes the heat balance within the video column and the capital investment required to handle the additional heat within the heat exchanger network. Secondly, the column top vacuum operating pressure could be increased from the design operating pressure to the maximum operating pressure at which the column is still able to accommodate a good separation to occur within the column. This reduces the amount of condensables and non-condensable at the vapor outlet of the video column to the ejector system, avoiding major modification to the ejector system and the associated steam, cooling water, and saltwater treating units. Thirdly, for all of the heat recovery pump around beds within the video column, there is the top pump around, middle pump around, and also the bottom pump around. High efficiency packing type with additional surface area could be selected. The heat recovery through the heat exchanger network could be optimized to achieve maximum heat integration within the video column, within the video unit through the use of high efficiency bed at both top pump around and middle pump around sections. And lastly, for all of the fractionation bed, packing bed within the video unit, the latest development in the technology of a hybrid pack bed could be chosen to provide better performance that is with higher void fraction without sacrificing the efficiency. So with the above optimization approaches, it was observed that the video column total internal vapor and liquid traffic was greatly reduced throughout the column while maintaining the product separation quality. The optimization also has resulted in smaller vapor condensables and non-condensables flows at the top of the column. This avoids major modification to the video column, its auxiliary system, and the heat exchanger network, hence significantly reducing the capital investment of the brownfield project. Okay, let's compare the modification scope with and without modification, or with or without optimization. Major differences are highlighted in the red boxes. Firstly, you could see that without modification, we need to increase the column diameter by 15% and the height by 10%. Technically, you need to replace this whole column to allow for this. Whereas if optimization is being performed, only the top pump around nozzle size need to be increased with the associated change in the spray distributor by about 25% increase in size. However, to avoid increasing the column diameter, and increase the column height, you can see that we need replacement of the top pump around, middle pump around, and bottom pump around section to high capacity type of pack bed without reducing the efficiency. And to do this, the latest development in the technology of hybrid pack bed was chosen. Other than that, you can also see that without optimization, replacement of LVGO pumps is required to as high as 150% additional capacity, comparing to only 40% increase if optimization is done. The bulk of differences actually lies in the additional scopes related to the associated system. As you can see that without optimization, first, we need replacement of the first stage ejector. And this comes with the associated steel structure for the new ejector system. And then we also need a new cooling water package and associated interconnecting piping. Thirdly, we also need a new steam generation package and associated interconnecting piping. And lastly, we need a new saltwater treating unit with an additional capacity of up to 60 ton per hour capacity. If we compare with the modification scope with optimization, only the replacement of the third stage ejector, which is a small ejector system, is required. Other than that, there will also be replacement of an LSWR and VR cooler to take out the heat duties from the VR stream at the bottom. So you can see that there's a huge differences between modification scope if we do or do not do optimization on the video column. And from our estimation, the cost associated with this additional scope is in the order of $25 million. I'm glad to share that in October 2019, the project with the proposed modification above has undergone a performance test run, and it is proven that it was able to meet the desired performance guarantee. So in conclusion, that optimization of a column operating condition and the design is critical, particularly for a complex column like a video column, especially when the column is already operating at rated capacity in a brownfield project. Also, we can say that based on the case study of a video column in an oil refinery in Malaysia, the study indicates that massive modification are required if optimization is not done on the column operating conditions, which add unnecessary capital expenditure and may render the project economically unviable. However, optimization of the operating conditions should be done cautiously with adequate verification work being performed, and this is to ensure that the column performance are not jeopardized and the performance guarantee can still be met by the project. With that, I would like to thank you.
Thank you very much, Ayah Saful, for the presentation. And we already have here two questions from the floor. The first one is, this is more for like asking for your opinion. Increasing top pressure will also reduce the yields and increase the residue. So the question is, what's your thought on this?
Hello, Assalamualaikum. Very good evening. Okay. On this, yes, apparently, you're right that increasing the pressure may affect the overall profile of the column. And it may, if we do not do anything, affect the yield of the individual product stream from this video column, and also affect the product specifications if nothing is being done. However, in order to maintain and ensure that the yield is still retained as per the desired or within the desired range, what needs to be done is that we need to allow more heat into the video column, to allow more vapor traffic to counteract with the additional liquid traffic with the increase in the operating pressure. At the same time, we need to allow more a better heat recovery within the column internals by having a higher efficiency internals, and also allow better heat recovery across the heat exchanger networks. So eventually, when the heat balance within the pump around and within the internals is back balanced, and then we can adjust the yield to return back within the design, the original design range. Yeah.
Okay, thank you very much. Actually, we have a third question as well, but having read both the second and third question, I think they are along the same line. So I guess I will just combine those two questions in which they are asking how much more optimization or additional capacity can be achieved for the video process just by performing process optimization without touching the hardware or the column inputs themselves.
I see. Okay. Okay. Just bear in. Okay. Thank you for this question. Just bear in mind that this column, that the video column that we were working on, has already gone a few debottlenecking, and it was already at its rated capacity. So we could say that it's already maxed out in terms of the capacity. So I would say that without any change in the hardware, the optimization will be very limited, probably between 1 to 2%. But that would require a very tight operation or operating envelope. So yeah, I think it's very limited in terms of the additional throughput that we could allow without any hardware modification to the existing column. Yeah. But if it's a newly built refinery where there's margin in place, yes, then apparently for this column, the throughput could be further pushed to a higher capacity, subject to the design margin that has been allowed for this column. Yeah. Okay. I hope that I answered the question.
Okay, thank you very much, Saiful. So I think that's all that we have questions for this presentation. And again, I would like to express my gratitude to Saiful for the very enlightening presentation. And that brings us to the end of this session this afternoon, Ps2 R2. And I hope all of you presenters and attendees alike have managed to learn a few things from the presentation and sharing. And probably we can bring them home and start applying all those knowledges that we have gathered this afternoon in our own work. And please do continue to communicate with the presenters for their opinions or for their advice if you have any further questions. Okay. And I guess I also would like to thank the co-chair, Prof. Aslinda from UTP, and also the moderators of the session, Dr. Azela. And I hope we'll be seeing you again for the next Icpeam event, I believe 2 years from now. And until then, please stay tuned and have a good rest for the rest of the evening. And I pass back the session to the moderator. Thank you very much, and me signing off.